Welcome to the Deep Dive. This is where we tackle some really dense research, pull out the core ideas, and basically give you a shortcut to getting up to speed.
Yeah, cutting through the noise.
Exactly.
Yeah.
So today, our mission is to look at cement. It's absolutely fundamental to, well, everything we build. And we need to figure out how this massive industry fits with climate goals.
It's a topic that often gets overlooked, I think. We talk energy, we talk transport, but cement, it's a quiet giant in terms of emissions.
It really is. And we're diving deep into one specific study today. It's called Trends in the Global Cement Industry and Opportunities for a Long-Term Sustainable CCU Potential for Power to X. Quite a title.
Ha! Yes, academic titles for you. But the content is crucial. It really lays out the scale of the issue.
It does. I was surprised, actually. Cement is the second most consumed product in the world. Okay, after steel.
Yeah.
Fine.
Right.
But it's production. We're talking about maybe 5% to 8% of all human-caused CO2 emissions.
Yeah, that number's huge. And this study points out something interesting that puts it just behind the chemical industry, but above iron and steel.
Above steel.
Yeah.
That really reframes it for me. And the core challenge, the study says, is just how much CO2 comes out per ton. About 866 kilograms.
And you have to break that 866 down. It's not all from burning fuel, not by a long shot. About half, 50% is what they call material derived.
Meaning it comes from the actual raw material.
Exactly. It's released when limestone, the calcium carbonate, KCO3, is heated and chemically transforms into lime. It's a fundamental part of the process.
So you can't just say, switch the kilns to run on green hydrogen or renewables and solve the whole problem.
Nope. You can tackle the fuel part, sure. That's maybe 40% of the emissions. Use renewables, carbon-neutral fuels, fine. But that 50% from the limestone, it's still there. It's unavoidable just by changing the energy source.
Okay. So after you've electrified everything, use green fuels, you still have this massive CO2 chunk left over.
Precisely. And that's why this study argues that carbon capture and utilization, CCU, is essential. Not just capture, but using the CO2.
Right. Because the study seems quite dismissive of just burying it, carbon capture and storage, or CCS. Why not just store it?
Well, they argue CCS is really tricky for cement. First, you need the right geology nearby, which isn't always the case. It's very location dependent.
Okay.
And second, the cost. They estimate CCS would basically double the capital and operating costs for a cement plant, just not economically feasible in most cases.
So burying it is expensive and difficult. Utilization, then, is key to making the economics work.
That's the core idea. That's the U in CCU and the power to X, or PTX, concept.
Okay.
You capture the CO2, then you use renewable energy, lots of it, mainly for hydrogen.
Through electrolysis, yeah.
Right, green hydrogen. And you combine that with the captured CO2 to make synthetic fuels, liquid fuels like synthetic gasoline or kerosene or synthetic natural gas.
And these synthetic fuels have value. They can be sold.
Exactly. So the idea is that producing and selling these fuels helps pay for the expensive carbon capture process itself, turning a waste stream into potentially a revenue stream.
Makes sense. What about the capture technologies themselves? What does the study favor?
They focus on two main ones. There's amine scrubbing. That's a known technology used in other industries.
But there's a catch.
Yeah, the flue gas from a cement kiln is really hot. Amine scrubbing needs cooler gas, so you have to spend energy and add equipment just to cool it down first. Adds cost and complexity.
Okay, what's the alternative?
The more perhaps integrated approach they discuss is calcium looping, or Cal-L. Especially interesting when combined with oxycombustion.
Calcium looping.
Yeah.
Does that use the lime itself?
Yes, that's the clever part. It uses lime, which is already part of the cement process, as the material that captures the CO2.
Oh, neat.
And even better, the lime that eventually becomes less reactive for capture. It can still be used as part of the final clinker product, the main ingredient in cement. It cycles back into the process.
That sounds much more efficient, potentially. Like a closed loop, almost.
Sort of, yeah. It integrates much better. But look, the study is realistic. They don't assume perfect capture overnight.
Right, the efficiency numbers.
Yeah, they project efficiency improving over time. Starting at maybe 60% capture before 2030, then ramping up to 70% by 2040 and aiming for 80% by 2050. It's a gradual tech improvement path.
A necessary ramp up. Okay, so we have a potential solution path with CCU and PTX. How big is the industry we're trying to transform? What's the global picture?
It's huge. As of 2016, the study counted over 2,300 operating cement plants worldwide.
Wow. Scattered everywhere.
Well, yes and no. Production is quite concentrated. About 83% of all cement comes from large plants, those making over 1 million tons a year.
And geographically.
Also concentrated. The top 10 countries account for something like 65–66% of global capacity. And China is the giant here, nearly 37% of global capacity alone.
37%, okay. And the study links future demand to GDP, right? That seems key to their projections.
Absolutely central. The core idea is that cement demand skyrockets when a country is in its main development phase. Building roads, airports, hospitals, cities, you need tons of cement.
Makes sense.
But once that major infrastructure is largely built, demand drops off significantly. It shifts more towards maintenance, replacement, smaller projects.
And they use that China example to illustrate this peak, don't they?
They do. It's an incredible statistic. China used more cement between 2011 and 2013, just 3 years, than the entire United States used in the whole 20th century.
Wow. Okay, that definitely shows a peak.
Right. That's what happens during that intense build-out phase. So based on this GDP correlation and development stages,
They project future global demand.
yes, they see global capacity demand rising to about 4,900 million tons in 2030. Then, crucially, it's expected to peak around 2040. The actual production number varies a bit by scenario, but around 4,500 million tons.
And after 2040?
It starts to decline, down to maybe 3,400 million tons by 2050, as more large developing nations move past their peak infrastructure phase.
Okay, so if cement production peaks around 2040.
Then the potential amount of CO2 you can capture and turn into fuel also peaks around 2040. That's the window of maximum opportunity identified in this study.
Got it. So let's talk numbers for that 2040 peak. What kind of synthetic fuel output are we looking at? This is where it gets wild, right?
Yeah, the potential is staggering. If we look at their business as usual scenario for cement demand, the captured CO2 could produce, well, it's a range.
Give us the range.
Okay, for synthetic liquids, PTL, like synthetic gasoline or jet fuel, somewhere between roughly 3,600 and 7,400 terawatt hours thermal.
TWH thermal, okay. And for gas?
For synthetic natural gas, SNG or PTG, the potential is even higher, between about 6,300 and 12,700 terawatt hours thermal.
12,700 TWHA. It's hard to even picture that number. How does that compare to, like, global energy use now?
Right, context is key. The study puts that maximum potential, the 12,700 TWH of gas, or the higher end for liquids, into perspective. They estimate that in 2040, this could potentially meet around 15% of projected global oil demand, or maybe 28%, almost a third of projected global natural gas demand for that period.
Hold on. Almost 30% of global gas demand from CO2 captured from cement plants.
Potentially, yes. That's the scale we're talking about, using recycled industrial CO2 to meet a significant chunk of global fuel needs.
That sounds almost too good to be true. There has to be a catch. And you mentioned it earlier, the energy input.
Ah, yes, the massive elephant in the room, electricity. Making the green hydrogen needed for PTX via electrolysis requires enormous amounts of renewable electricity.
Enormous.
The study projects the additional electricity demand needed just for this PTX process. By 2050, for the liquid fuels route, PTL, it could be up to around 12,200 terawatt hours electric.
12,000 two-wheel.
And for the synthetic gas route, PTG, it's even higher, up to nearly 16,700 terawatt hours electric.
16,700. That's more than current global electricity consumption, isn't it? Or close.
It's a monumental amount of additional clean electricity. It fundamentally changes the scale of the energy transition needed.
So how is that even possible? Does the study address feasibility?
Absolutely. They are very clear. This whole concept relies on a future energy system absolutely dominated by cheap, variable, renewable energy. Think solar and wind.
So you need times when electricity is almost free because there's so much renewable generation.
Essentially, yes. You need periods of very low-cost electricity to make the electrolysis for hydrogen economically viable at this scale. It assumes a radical transformation of the grid and energy market.
Okay, a huge challenge, but the potential payoff is also huge. Now, if this does happen, where geographically does this PTX potential emerge? You said production shifts.
Right. The map changes dramatically over time. Northeast Asia, dominated by China now, sees its share of this PTX potential fall quite sharply, from nearly 40% in 2015 down to less than 17% by 2050.
Because their major build-out phase is ending.
Exactly. Europe and Eurasia also see significant drops, maybe 30–40% reduction in their share of the potential. They're mature markets, too.
So where's the growth happen? Where does the PTX potential boom?
The biggest growth by far is projected for sub-Saharan Africa. The study suggests an 800% increase in its synthetic fuel potential from cement CO2 by 2050 compared to 2015.
800%.
Yeah. And also significant growth in South Asia, the SAARC region. It follows that GDP infrastructure correlation perfectly. The big building booms are shifting south.
Fascinating. So the future of this specific decarbonization tech is tied to development in Africa and South Asia.
Largely, yes.
Yeah.
That's where the peak CO2 availability will be in the coming decades.
Okay, let's touch on economics again, sourcing the CO2.
Oh.
You said CCU helps pay for itself via the fuels, but how does the cost of getting that CO2 from a cement plant compare to, say, sucking it directly out of the air, direct air capture, DAC?
Ugh, good question. There's a big cost advantage for cement CCU, according to this study, because the CO2 is much more concentrated in the flue gas, maybe 15–30% concentration, versus 0.04% in the air.
Much easier to grab.
Much easier, less energy needed per ton. So the cost range they estimate for cement CCU is somewhere between $13 and $124 per ton of CO2 captured.
$13 to $124.
Okay.
Okay.
And DA costs.
Currently much higher. The study cites ranges like $150 to $300 per ton, though DC companies are aiming lower, maybe $75 actually.
So even with optimistic DC projections, getting CO2 from cement flue gas looks significantly cheaper.
Yes, for the foreseeable future, cement plants represent a much lower cost source of concentrated CO2 for making these synthetic fuels.
Right, which brings us to the final kind of philosophical carbon question. You capture CO2, great. You make fuel, okay. But then you burn the fuel, and the CO2 goes back into the atmosphere. Have you actually avoided emissions or just delayed them?
That's the million-dollar question, isn't it? And it's critical. The study's argument is that the primary benefit is displacement.
Displacement of what?
Displacement of extracting, refining, and burning new fossil fuels dug up from the ground. By using recycled carbon from the cement process, you avoid the emissions associated with that whole fossil fuel value chain.
So it's a net reduction because you're replacing virgin fossil carbon with recycled industrial carbon.
Exactly. The study estimates that implementing this CCU PTX pathway could reduce the total life cycle emissions from cement production by about 70% compared to just continuing business as usual. It's not zero emissions, but it's a massive reduction.
Okay, 70% reduction by avoiding fossil fuel use. That's a very significant benefit, especially during the transition period.
It's a crucial way to leverage an otherwise unavoidable industrial emission. Makes you rethink what waste CO2 really is.
Absolutely. Okay, let's try to wrap this up for everyone listening. What's the big picture takeaway here?
Well, we started with cement, fundamental product, huge CO2 problem, and about half of it is unavoidable just by changing energy sources.
Right, the process emissions from limestone are the real challenge.
Then we saw that capturing that CO2 and using it to make synthetic fuels, the CCU-PTX route, seems like the most viable path forward, both technically and crucially economically.
But, and it's a huge but,
Right.
it relies entirely on a future flooded with cheap renewable electricity to make the hydrogen.
A massive energy system transformation is baked into this solution, and we saw the geography shifts. The future hotspots for this potential are sub-Saharan Africa and South Asia, following the infrastructure booms.
It aligns decarbonization with development, in a way?
In a very direct way, yes. So we've really gone through the key findings of trends in the global cement industry and opportunities for a long-term sustainable CCU potential for Power to X.
We have, and I want to leave you, our listener, with one final thought to chew on, drawn from the study's implications. Even if we realize the maximum potential for synthetic fuels from cement CO2 around that 2040 peak, the study suggests that just the demand for oil and gas for non-energy uses, think plastics, chemicals, fertilizers, that non-fuel demand alone might exceed what cement CCU can supply.
Interesting point.
So if even this massive PTX potential from cement can't cover the feedstock needs for basic materials in the future, where does that essential carbon come from then? Is expensive direct air capture the only other option left on the table?
Definitely something to think about as we watch how industries source their carbon in the decades ahead.
Food for thought.
Yeah.
We'll catch you on the next deep dive.